picture this. You are standing in the middle of a massive warehouse-sized room. The air conditioning is just blasting.
Yeah, it's incredibly loud in those places.
Right, exactly. It's just this constant, deafening hum of commercial cooling fans. And stretching out in front of you, like as far as you can see, are rows and rows of metal racks.
Packed floor to ceiling with black boxes.
Yeah, heavy-duty fiber optic cables cascading down the sides. Thousands upon thousands of blinking link lights. I mean, it really looks like the physical, tangible embodiment of the internet.
It is. I mean, that is the modern data center.
Yeah.
And while it is incredibly tempting to just stare at all that expensive hardware and the flashing LEDs, the metal itself is, well, it's essentially just dumb iron.
Right.
The real magic, the actual engine of modern connectivity, is the invisible ecosystem of software and protocols running on top of it.
And that invisible ecosystem is our entire mission today. Welcome to the Deep Dive. We're taking you on a mental walk through one of these data centers, rack by rack, to look under the hood.
It's going to be a fascinating trip.
Yeah. We're using a stack of notes and technical breakdowns from Professor Messer's CompTIAA plus IT certification training courses, specifically zeroing in on network services.
Right.
We all know the basics. We know what an IP address is. We know what a URL does. But today, we want to dissect the sheer mechanical complexity of the background labor that happens in the milliseconds between you hitting enter and a web page actually loading.
Because we tend to hyper-focus on the physical endpoints. The smartphone in your hand or, the laptop on your desk.
Yeah, the shiny stuff.
Exactly.
Yeah.
But a device without network services is just an expensive paperweight. I mean, these services handle the identity, the navigation, the cryptographic baselines, and the security of literally every packet of data you generate.
So let's start with the foundational handshakes. Because before a device can pull down an email or, query a database, it has to negotiate its way onto the network.
It needs an IP address.
Right, which means it needs DHCP, the Dynamic Host Configuration Protocol. And look, we all know DHCP hands out IP addresses, but the source material highlights how this operates at an enterprise scale, which is an entirely different beast than the little Wi-Fi router sitting in your living room.
Oh, absolutely. When you are dealing with a corporate environment or like a massive cloud architecture, you aren't just assigning IPs to a few dozen laptops.
Right, it's way bigger.
You might have an automated system spinning up 5,000 virtual machines for a temporary stress test and then spinning them down an hour later. So DHCP has to manage these massive pools of addresses dynamically.
It's constantly juggling.
Exactly. It utilizes mechanisms like rapid lease times, where an IP is only loaned to a device for a few hours. When that device leaves the network, the DHCP server reclaims the IP and throws it back into the pool to prevent IP exhaustion.
And if that DHCP server goes down, the entire network just grinds to a halt because new devices literally cannot join.
Which is a nightmare.
Right. So administrators build in massive redundancy. Multiple DHCP servers operating in failover relationships, constantly updating each other on which addresses have been leased out, ensuring no two machines ever get assigned the exact same IP.
And once you have that IP address, you have a valid identity on the network. But you still need to know how to navigate. You need to translate the human-friendly domains you type into your browser into the machine-readable IP addresses of the destination servers.
Which is the domain name system, DNS. Now, I've often heard DNS described with the tired cliche of being the phone book of the internet.
Yeah, you hear that one a lot.
But reading through these architectural notes, that metaphor feels way too simple. I mean, a phone book is a single static object. DNS operates more like a high-speed, globally distributed postal routing system.
That's a much better way to visualize it. DNS is not one centralized database sitting in a server rack in California. It's a hierarchical, distributed platform.
So it's spread out everywhere.
Exactly. When you query a domain, your request doesn't usually travel all the way to the authoritative server for that website. The system relies heavily on edge caching.
Right, so it remembers things.
Your local internet service provider, or even your own computer's operating system, memorizes the IP address from the last person who asked for it.
So it caches the result based on a time to live, or TTL, value. The local node essentially says, hey, I'll remember this route for the next 24 hours to save time.
Yeah, that's how the internet manages the sheer volume of billions of DNS requests a second without just collapsing under its own weight.
It's pure efficiency. But there's a third foundational protocol running in the background of these handshakes that is almost entirely invisible to the user, and that is NTP, the Network Time Protocol.
Yes, NTP. Crucial.
Okay, let's unpack this,
Yeah.
because when I first looked at the network service diagrams, I kind of wanted to push back on the inclusion of NTP.
Really? Why is that?
Well, I understand that my computer syncs with the time server, so my calendar alerts fire off properly, right? And so system administrators have accurate timestamps when they are trying to correlate server logs. But dedicating massive, highly resilient network infrastructure just to keep the clock synchronized down to the millisecond.
It seems like a lot.
Yeah, it felt like overkill. I mean, does it really matter if my laptop is off by 4 seconds?
What's fascinating here is that it matters immensely because time synchronization is the absolute bedrock of modern cryptography.
Like cryptography.
Yeah. When your computer attempts to establish a secure, encrypted connection with a web server, let's say you're logging into your browser and the server exchange cryptographic certificates.
Okay.
And those certificates contain strict time-stamped parameters.
So if my computer thinks it's 2:00 p.m., but the bank server knows it's 2:05 p.m.,
The server will immediately reject the connection.
just flat out reject it.
From the server's perspective, a timestamp that is out of sync by even a few minutes looks exactly like a replay attack.
Ah, a replay attack.
Right. It assumes a malicious actor has captured an old packet of data and is trying to resend it to gain unauthorized access. So if the clocks aren't perfectly aligned via NTP, the TLS handshake fails, the encryption protocols break down, and you are entirely locked out of the secure web.
Wow. That completely flips the script on how I view the little clock in the corner of my screen.
It's not just a convenience feature.
No, it is the linchpin holding the security apparatus together. So, okay, the device is on the network, it knows the routing via DNS, and its cryptographic baseline is set via NTP. Now we get to the daily grinders, the actual applications doing the heavy lifting.
Right, the stuff people actually use every day. Web servers handling the HTTP and HTTPS requests, and email servers routing SMTP traffic.
Right.
And, the notes from Professor Messer emphasize a fascinating reality about email architecture in particular. It has arguably the most brutal uptime expectation of any network service.
It makes sense when you think about corporate culture, though. I mean, if an internal file server goes offline for 15 minutes, the department might grumble and go grab a coffee.
True. But if the corporate email server drops for 15 seconds, it is treated as a catastrophic outage. Users tolerate zero downtime for email.
Which means administrators have to design email infrastructure with aggressive redundancy.
They can't let it fail.
No. They use multiple mail exchanger, or MX, records in DNS, pointing to backup servers located in entirely different geographic regions, just so a localized power outage doesn't bounce a critical client email.
And speaking of internal file servers, that's another massive daily grinder. Centralized storage where thousands of employees are accessing and saving data simultaneously.
Yeah, that's a huge load.
In Windows environments, this operates on SMB, the Server Message Block Protocol, and in Apple environments, it's AFP. But the real engineering challenge here isn't just storing the data, it's managing the collisions.
Because imagine two executives opening the exact same financial forecast spreadsheet from a central server at the exact same moment.
Yeah, man.
If they both start making changes, whose changes get saved?
Right, it would be chaos. So SMB utilizes complex file locking mechanisms. It allows the first user to have read-write access, while dynamically negotiating a read-only state for the second user. That prevents massive data corruption across the network.
And the same principle applies to print servers, right? Using protocols like IPP, the Internet Printing Protocol, or LPD, the line printer daemon. It's all about queuing and negotiation.
Absolutely.
But the undisputed king of these daily grinders has to be the database server running SQL structured query language.
No, without a doubt. Relational databases are the backbone of virtually every major application on the planet. Instead of storing data in flat files, SQL allows you to build incredibly complex relationships between distinct tables of data.
So it's not just a giant list.
No, you can instantly query millions of customer records, cross-reference them with regional sales data, and return a specific output in a fraction of a second.
Here's what strikes me about all these grinders, though. SMB file locking, LPDQ negotiations, SQL relational joins. A normal user on an average Tuesday never sees any of this.
No, they don't.
To the user, modern operating systems act as an incredibly thick abstraction layer, like a highly polite concierge. The OS hides all these wildly complex, messy protocols behind a simple graphic of a floppy disk. You just hit save.
Because the ultimate success for a network engineer is absolute invisibility. If the user has to think about how the LPD protocol is routing their print job over a segmented subnet, the engineer has failed.
That's a great point. But centralizing thousands of gigabytes of proprietary corporate data on SMB shares and SQL databases creates the ultimate target. You can't just let anyone who plugs a laptop into a wall jack access the financial records.
Which brings the entire architecture to the watchdogs and the gatekeepers. Security isn't just an afterthought, it is integrated into the routing itself. And the very first barrier is the AAA server authentication, authorization, and accounting.
Now, we know authentication is proving who you are, authorization is what you have access to, and accounting is logging your actions. But in an enterprise environment, this isn't just checking a password against a local text file.
Far from it. An enterprise AAA server, using protocols like Radius or TAC-XS plus CAC-S, acts as a centralized cryptographic authority.
Okay, how does that work?
When you log in, the AAA server validates your credentials and issues a cryptographic token or ticket. So when you try to access that sensitive SQL database we just talked about, you don't send the database your password.
You send the token instead.
Exactly. You present the token. The database trusts the token because it trusts the AAA server.
But if the AAA server is the master key to the entire kingdom, the scale of that infrastructure must be massive compared to a home network. I mean, at home, you share a single Wi-Fi password. It's a flat network of implicit trust.
Enterprise networks operate on zero trust. And because every single request from opening a file to accessing a web portal requires AAA validation, you have to run heavily redundant AAA clusters.
Because if it goes down...
If a single authentication server fails without an immediate failover, 10,000 employees are instantly paralyzed. They can't check their email, they can't print, they can't access their own files.
So the user authenticates, and the AAA server grants them the token. But trust isn't a one-time check. The network has to constantly monitor what that user is actually doing once they are inside.
That's the accounting piece.
Right, which requires a massive aggregation of data via syslog and SIME.
Yes, because every device in that warehouse-sized data center, every router, switch, firewall, and server is constantly generating text-based logs of everything that happens.
And mountains of data.
And syslog is the standard for taking all those disparate logs and forwarding them to a central, massive database, typically a SIEM, a security information and event manager.
And the SIEM doesn't just store the logs, right? It correlates them. It builds context.
If we connect this to the bigger picture, imagine a firewall log shows a successful VPN login from an IP address in Tokyo.
Okay.
3 minutes later, a physical security log shows that same user's ID badge swiping into the lobby of the Chicago office.
Oh!
These are two isolated systems operating normally. But the SIEM correlates those two events, recognizes the impossible travel time, and instantly triggers a high-priority security alert.
That kind of correlation requires analyzing millions of lines of data in real time. It explains why syslog servers demand such massive storage arrays. You aren't just looking at today's traffic. You need months of historical data to establish baseline heuristics so the SIEM knows what abnormal even looks like.
Precisely. And while the SIEM is watching internal behavior, you have proxy servers and UTMs managing the perimeter.
Okay, proxies.
When a user tries to access a website, they rarely make a direct connection to the outside world. The proxy server intercepts that request, it goes to the website on the user's behalf, pulls the data down, inspects it, and then hands it back to the user's browser.
Let me push back on that process for a second, because most of the web is encrypted now with HTTPS. So if a proxy is sitting in the middle, intercepting my request, unpacking the encrypted data, looking at it, and then repacking it, isn't the proxy essentially performing a man-in-the-middle attack on its own employees?
From a purely cryptographic standpoint, yes. That is exactly what enterprise TLS inspection is.
Wow.
The company installs a trusted root certificate on the employee's machine. This allows the proxy to seamlessly decrypt the traffic, inspect it for malware or corporate data exfiltration, re-encrypt it, and send it along.
And often those proxy functions are rolled into all-in-one security appliances or UTM's, Unified Threat Management Systems. Instead of having a standalone firewall, a separate spam filter, and a distinct bandwidth shaper, the UTM handles it all.
It's super efficient.
Yeah, it can perform URL filtering by checking requests against dynamically updated global threat intelligence feeds in real time. It can sandbox suspicious file downloads, detonate them in a virtual environment to see if they are malicious, and block them before they ever reach the user's hard drive.
But inspecting individual packets with UTMs and proxies requires immense processing power. And surviving a massive, sudden influx of millions of legitimate packets is an entirely different engineering challenge.
Which introduces the traffic cops of the data center, load balancers. Here's where it gets really interesting because I absolutely love the mechanics of load balancing.
Is brilliant engineering.
When an organization builds a web server farm to handle high traffic, they place a load balancer in front of it. But it doesn't just blindly deal out connections like a car dealer. It operates more like a highly observant restaurant expediter.
Yeah, the expediter knows exactly which chef is overwhelmed and which one has capacity. A load balancer constantly monitors the health of every server in the farm using heartbeats.
Heartbeats.
It sends a tiny ping to each server every millisecond.
And if a server suddenly experiences a catastrophic hardware failure, like the motherboard literally catches fire, it misses a heartbeat.
Right.
The load balancer instantly senses that failure, pulls that server out of the rotation, and seamlessly redistributes the incoming traffic to the surviving machines. The end user, sitting on their couch clicking a link, has absolutely no idea a major hardware failure just occurred.
That seamless continuity is vital for web traffic. But the stakes change dramatically when those servers aren't just serving up HTML, but are actively controlling physical forces in the real world.
Like actual machinery.
Yes. That brings us to SCADA, Supervisory Control and Data Acquisition, or ICS, Industrial Control Systems.
So we are talking about the network architectures that manage power grids, oil pipelines, municipal water treatment plants, and robotic manufacturing lines.
These systems use specialized hardware like programmable logic controllers, or PLCs. These translate digital network commands into physical mechanical actions, like opening a massive pressure valve or increasing the rotational speed of a turbine.
Wait, so the same underlying network architecture handling HTTP requests and SMB file shares is running municipal water supplies. That seems incredibly dangerous.
It is. Which is why the absolute foundational security doctrine for SCADA systems is network segmentation.
So keeping them separate.
Yes, an air gap, or at least a heavily fortified logical boundary.
Yeah.
You cannot have the PLCs controlling the factory floor sharing a network with the corporate accounting department.
Because if they do,
If they share a network, a single employee clicking a phishing email could theoretically give a malicious actor a pivot point to access the industrial controls.
and a cyber attack on a SCADA system doesn't result in stolen credit card numbers. It results in a burst pipeline or regional blackout. The digital bleeds into the physical.
Which perfectly transitions us to the final and perhaps most surprising reality of these environments. We spent this entire time visualizing a pristine, hyper-modern data center humming with new technology.
Yeah, all the blinking lights.
But the truth is, a corporate network is full of skeletons in the closet. You have the oddballs, legacy systems, embedded systems, and the Internet of Things.
Okay, let's talk about legacy. The source material points out that you will find servers installed 15 or 20 years ago still running in modern server racks. My initial reaction is that keeping ancient hardware online is a massive negligent liability. Why not just upgrade?
Because upgrading is often a higher risk than maintaining the legacy system.
Really? How so?
Well, that 20-year-old server might be running a highly specialized proprietary piece of software, perhaps a compiler for a legacy aerospace component that the original vendor hasn't supported since 2008.
Oh, I see.
The company relies on that software to survive, and migrating it to modern hardware breaks the code. So the system administrator has to build heavily monitored, segmented cages around the legacy box to keep it alive and secure.
That makes sense. You also have embedded systems, right? Purpose-built devices like automated fire alarms or digital time clocks, they don't have a standard operating system you can log into.
No, they're basically black boxes.
Provided by a manufacturer, designed to just sit on the network and run quietly.
And embedded systems are generally stable. The real wild card, the nightmare scenario for modern network administrators, is IoT, the Internet of Things.
Smart refrigerators in the break room, network-connected HVAC thermostats, Wi-Fi doorbell cameras. Every single appliance demands an IP address now.
And this requires a massive shift in how we view risk. The companies manufacturing these smart appliances prioritize functionality. They want the fridge to tell you when you're out of milk.
They don't care about the firewall.
Exactly. They historically do not prioritize enterprise-grade network security. They ship devices with hard-coded default passwords, they rarely issue firmware updates for vulnerabilities, and they often transmit telemetry data using unencrypted protocols.
I remember reading about a massive retail data breach several years ago where hackers didn't attack the heavily defended payment gateways directly. They found an unpatched vulnerability in the smart HVAC systems controlling the store temperatures.
The classic example.
Yeah. Because the network wasn't properly segmented, the hackers used the thermostat as a bridgehead. They compromised the HVAC unit, used its network access to pivot into the corporate Active Directory, and ultimately stole millions of credit card numbers.
That is the exact threat model. You have to treat IoT devices with the same paranoia as a legacy system or a SCADA environment.
Segment them off.
You isolate them on a dedicated, segmented subnet. You restrict their access strictly to the internet gateways. The smart TV can stream video. But you put hard firewall rules in place preventing that TV from ever communicating with the internal file servers.
So you are actively isolating the convenience of modern smart appliances to protect the critical core of the business.
Because a network is only as secure as the weakest link physically plugged into it.
We have dissected an unbelievable amount of invisible labor today. I mean, from the initial DHCP IP assignments and DNS routing to the cryptographic bedrock of NTP.
That's a lot to take in.
We've looked at the file locking mechanics of the daily grinders, the centralized token architecture of AAA, and the correlation engines of the SIME. We've seen load balancers checking heartbeats and SCADA systems bridging the digital and physical worlds, all the way down to the segmented cages holding 20-year-old legacy servers and deeply insecure smart thermostats.
It is a meticulously orchestrated ecosystem. Millions of automated decisions, packet inspections, and cryptographic handshakes occurring simultaneously to create the illusion of a seamless user experience.
So the next time you casually type a URL into your browser and hit enter, take a second to appreciate the sheer mechanical complexity that just executed perfectly in a blink of an eye to bring that page to your screen.
And consider this as you look at the evolving landscape. As our built environment increasingly relies on IoT, devices engineered for convenience rather than security, are we essentially building the future of our digital infrastructure on a foundation of highly vulnerable coffee makers and refrigerators?
That is a scary thought.
How long can our segmented subnets truly hold the line between the systems that keep our critical data safe and the appliances that just want to connect to the Wi-Fi?
That is a complex problem that every network engineer is currently wrestling with. You will definitely look at the smart devices in your own home a little differently today. Thanks for joining us on this exploration of the invisible internet. Next time you picture that massive room full of glowing server racks, you'll know exactly the kind of hidden labor going on inside the hum.